Okay, so so let's start then with SymPy. You have the link already over here in this section here. So this is the tutorial. So SymPy, right? So SymPy is for symbolic Python, and it's kind of a funny thing. I don't know if many of you have heard of Mathematica and Wolfram Alpha, this kind of software, right? So what does this do? It does calculations, not in the sense of taking numbers and calculating, but it actually does algebraic calculations as you do by hand, right? So you can take polynomials and expand or factor expressions and calculate derivatives, integrals, limits. It can, if you do divide a matrix, it can calculate Jacobians and do solve equations and do a lot of stuff that you do usually by hand, okay? And of course, you can, if you have seen this before, right? So let me just show you what people, I think that the most common, the most famous one, I think, is Wolfram Alpha, okay? So here it is, so yeah, never type it. Yeah, so this is the thing here, Wolfram Alpha. I don't know, many of you have seen this, or for instance, do something like, yeah, something like this, right? So you type here and it gives you the solutions, right? So, yeah. You see here, and and it kind of interprets what you type and then gives you the solution, right? So this seems pretty convenient, right? So why do this with SymPy and Python and so on that looks a bit more involved, right? The thing is that it's very useful to have a tool that you introduce expressions, and then you have this in the computer available to do other calculations on top of that, right? So it's Wolfram Alpha, you have to do a lot of copy and pasting, and if you want to use it in your program that is, I don't know, plotting, or you have to do some other numerical calculation, as we will see in the rest of the course, you have to keep copying and pasting and have type errors, and so it's very practical to use to do these calculations inside the same environment as you already do the rest of your stuff, okay? So so what does SymPy do then, right? So let's this will be a simpler tutorial than the previous one. It's essentially a few functions that of what SymPy does, and the main thing here is, okay, we have a variable. What is an x, a variable in the mathematical sense? Well, I think at this point you already have a more or less clear picture that a variable in a built-in environment is very different from a variable in math. Okay, if I say in math I write some x equal 1, and then I change, or x equal y, and then I change y, I'm not changing x together, right? So this is pretty simple, right? So it's not the same thing. A variable in math is different from a variable in the computing sense, okay? But then in SymPy we will call a variable in the math sense, right? A symbol, okay? A symbol. For instance, here, so SymPy, you import it like this, import SymPy as we did before. I'm going to not import all of the functions inside SymPy. I'm going to import it with this name sp. And you have this function here, symbols, that creates symbols, okay? So here, creating the symbols, I have to pass a string separated by commas, the names of the symbols, okay? And then I assign this to variables. So this here is the name of the symbol, and this here is the variable in the sense of a Python variable, okay? I would, this is very weird. Let me just run this just to see what happens here, okay? But you could do something very weird here, that is calling a variable by a different name, and it doesn't matter, right? So let me show you an example of this, right? Just to not confuse, let me create a new thing here. So I would say that, for instance, I create a symbol. Oops. I create a symbol here called, I don't know, called Z. Okay, but then I call this A. Okay, I can call this A, it doesn't matter, right? When I do A squared, what do I see here? I see Z squared. Okay, because the symbol name is Z, but then I assign to it the variable called A. Okay, this is very confusing if you do this, so I usually try to avoid this, right? It's much better to have the symbol name X being attributed to the variable name called X as well, right? So that you don't confuse stuff. But these are different things, okay? The symbol and the variable, okay? Good. And then with this symbols here, what can you do? You can write down expressions, right? So what is an expression? Simply any function, not a function not a function in the computing sense of a Python function, a function in a mathematical sense, okay? So if I combine variables, for instance, I take x plus y squared, right? I have this thing here, minus 2, I can do any operation here, okay? So you see, and when you print this, you see that you have exactly those expressions, okay? So far, so good, okay? Simple question so far. Okay, so, yes? Can you use the mic, please? I think it's here. Yeah.
When you did the first one, not the first one. When you showed Z squared, why like that? Why
okay. I will tell that in a moment. Yeah.
Okay.
The printing, right? Why this is so nice and this is ugly? That's the question. Yeah. Okay. In a moment. Okay. Okay, printing. This is exactly what we're going to talk about next. So if you do print, it will print the expression exactly as you wrote it, right? Not exactly. It can change the order sometimes, okay? But it won't change the structure of the expression you have, okay? And it will be like this, in the same way that you would type it back to define the expression, right? So if I just copy this here and put this back here, is exactly the way I defined it, you see? Yeah, so if I print an expression, it gives you a string that is the one that I would use to define this expression, okay? But then if I want to see this in a more pretty way, okay, you have a few functions, right? So there's this function pprint that is for pretty printing, that is still plain text, okay? We have this display function, that this is the one that gives you a pretty, a nice visualization. I'll see in a moment. And finally, if you use LaTeX, I don't know how many of you have used LaTeX before. Probably the mathematicians and physicists, right? Pretty much all of them, I hope. Yeah? Yes or no? Yeah? So a few of you that use LaTeX, you can also call the function LaTeX and an expression inside, and then it will return the LaTeX code for that expression, okay? So for examples here, right? So you have this init printing function that you call in the beginning, right? And you import this display function from the IPython display, okay? So you do this. Because if I just type this here, it uses this display function internally, okay? But if I want to display it in the middle of the text, I have to import this function display here, okay? This is not inside SymPy, it's a function of the notebook, okay? So I import display, I do this init printing so that SymPy recognizes the environment it is in, okay? So for instance, if you are in a pure Python, it will print in a certain way. If you are in a notebook, it will print in a certain way. If you are in an IPython shell, it will print in a different way. So depending on the environment where you are using it, it tries to choose the best option to display. Okay, so this is what this function here does. Usually you do this when you first import SymPy, just to get it to recognize the environment. Okay. Now, if you run this now, okay, I'm going to take the expression 3 here, and I'm going to print it in different ways, okay? So if I p-print it now, it looks like this, right? So this is still pure text, okay? This is pure text, but you see that it's made in such a way that it looks a little bit nicer, okay, than remember this one here. You see? There was this one here that doesn't look nice at all. And there's this one that is still pure text, but it's a little bit nicer. And now there's the display one that is the really nicest one, okay? Then this looks more or less professional type setting, okay? Yeah. And finally the LaTeX one, okay? So the LaTeX one, if you include this LaTeX one in a LaTeX document, when you compile it, it will look like this, okay? Yeah? Yeah, this is your question, right? So, yeah, fine, nice. So you can do stuff just by you use LaTeX code. It's already a bit useful, okay? Now, what can you do with these expressions, right? So you can expand and simplify in factor. So, for instance, let's do some examples, okay? So, for instance, x plus y squared. If I call this expression 1 here, if I expand expression 1, I get expression 1xp. If I display this, I just open it, okay? Yeah, so it does it for you, okay? So I just have to use this function expand, and the expression is as an argument, okay? In the same way, you can factor, okay? So if I take this expanded expression here, okay, I expand it. If I want to factor back, I call the function factor on this expanded expression, okay? And now I have the factored expression. And the factored expression is just the original expression back, okay? Yeah, so you can factor, you can expand. What else can you do, right? And you can simplify. What is simplifying, right? So this is more heuristic, okay? Because simplifying sometimes there's no mathematical definition, rigorous definition of what is simplifying, right? Of course, if you have terms that can cancel out, you cancel them out. But sometimes it looks simpler if you put everything together in a single fraction. Sometimes it looks simpler if you separate them out. It's a bit complicated, okay? There's no single definition, okay? But usually it does a good job, but there are exceptions, okay? So for instance, right? I have here sine squared plus cosine squared. When I simplify this, so I call simplify in this expression here, okay? Sine squared plus cosine squared, and it simplifies to 1, okay? So it can uses trigonometric identities and so on and so on, okay? Now, if I take this other expression here, right? So this x cubic plus x squared plus minus this fraction here, okay? So this is the original expression over here. When I call it to simplify, what does it do? It recognizes that there's a common factor between the numerator and denominator, cancels out this common factor, and gives you x minus 1. Okay? Nice, right? Yeah? Nice. But then there are some exceptions, right? So here is an expression. I think this is expression 3, right? So you have this thing here. It doesn't look too simple, but then when I try to simplify this expression here, okay, it gives us this, right? That I would argue that it doesn't really look simpler than the original one, right? So, yeah, you see? So, this is the best it could do, okay? Okay, yeah. So, it's usually useful to try to simplify, but sometimes it doesn't go the way the way you expected or wanted, okay? Another function that is useful is this apart that essentially does partial fractions. I don't know, some of you may have heard of this in calculus courses, but essentially what is a partial fraction? It's looking at a quotient between two polynomials, right? And then you factor the polynomial in the denominator, and then you separate your expression into fractions that have these factors of the denominator here, okay? So this is, I'm not going into detail here. If you know, if you know this and know how this can be useful, okay? If you don't, it doesn't matter so much, okay? But yeah, So this is the apart function, okay? And finally, collect, okay? Collect is nice in terms of if you have an expression and you want to collect all powers of a certain variable, then it does that for you, right? So here I'm looking at this expression here, okay? And I want to collect the powers of x. So when I do collect expression and the name of the variable I want to collect, right? Because I could have many more variables, right? So I could collect in terms of powers of x or powers of y, powers of any variable, okay? Then it gives me x cubic, x squared times the factor, x times the factor minus 3. So you see that you have very well organized all the powers of x, okay? Yeah, so this is what collect does, okay? Good, so this is pretty much only simplifying and organizing expressions, okay? What can we do in terms of really actual math here, right? So nice math. The first one is solving algebraic equations, right? Solving equations like f of x equal to 0, okay? So here I'll give you some examples, right? So usually you have this function solve, okay? And solve, what do you pass to solve? You have two arguments. You have an expression, and this expression is always, this expression is equal to 0, okay, when you pass an expression. So if you have something on the right-hand side, I don't know, if I want to say solve x plus 1 equals x squared, you have to pass x squared to the left-hand side so that the right-hand side is 0, okay, right? And then the second argument is the variable that you are solving for, okay? So if you have, for instance, x plus y, right, equals to 0, then x is equal minus y, right? This is the solution for x, but if I wanted to solve for y, then y equals minus x, okay? So you have to provide which variable you're solving for, okay? Well, let's try to run this, right? So in the first case here, I solved x plus 1 equals 0 like this, you see? So this is the old I had here, and of course x equals to minus 1 is the only solution. The solve function always returns a list of solutions, okay? In this case, there's a single solution, so it's a list with a single element, minus 1, okay? For instance, now if I do this equation here, right? So this is a second degree equation. It has two solutions, 1 and 2, you see? Here it is. Now if I want to solve something a bit more complicated, right? So this cosine of x minus y equals 0, okay? For x. When I solve this, it gives me what? It gives me something involving the arc cosine of y plus 2 pi arc cosine of y, right? So this actually is a bit of an, actually have infinite solutions of this, right? Because you could have cosine is a periodic function and so on, right? This is why there, it shows two solutions. There were even more actually, but yeah. So it's not perfect in the sense of if you have infinite solutions, it doesn't necessarily give you back all the possible solutions, especially for trigonometric equations, where you would expect infinite solutions. Sometimes it doesn't give you all of the solutions. Okay? There are other functions in SymPy that try to do this, but solve doesn't, okay? Usually, I'm not going into more detail here because usually we are interested in only a single solution or just a couple of solutions, okay? Not all the infinite solutions, okay? And finally, I have an example here that is a bit more fun. Exponential of x minus 2y equals 0 gives me the log of 2y. And if I solve now x, you see that there's an x here, okay? X times exponential of x minus 2y equals 0. Now I have something that is not really solvable with the methods that we learn in school, but it's solvable in terms of this function w here, okay? W is a special function. It's called the Lambert W function. That is a special function that you may never heard about, but SymPy did, so SymPy solves it for you in terms of also special functions, okay? Yes?
Is there a way to solve an equation for a given range of x? So you can look for solutions in the range you want?
Not directly from solve. Then usually you have to look at the solutions and check if they're in the range you want, okay? So there's no way to directly restrict the range, okay? One thing that I didn't talk about is that the default type of symbol, so X and Y here for instance, by default assumes that this will be complex, okay? So if you have a solution that is complex, it will give you complex numbers, okay? You can restrict, when you define the symbol up here, you can define, then you have a keyword when you define the symbol, that you can pass something like real equals true, okay? And then if you ask for the solution for X and Y, and it is complex, not real, then it will not give that as a solution, okay? Yeah, but not restricting to range. No, this you have to do yourself later, right? You get the solutions and then you check if it is in the range you want, okay? Okay, so going back down, so algebraic equations, this is it, okay? And of course, there are equations that don't have solution. In this case, it doesn't solve it, okay? It just returns back the equation for you, okay? Now, let's do a bit of calculus, okay? Calculus, so derivatives, integrals, and limits, okay? So these essentially are these three functions here, GIF for the derivatives, integrate for integrals, and limit for limits, okay? Okay, so let me go first for derivatives. So if I take, for instance, this function here, okay, I take this thing here. I skipped the first example, maybe. I went directly to a complicated example here. Okay, sorry. Let me start with a simpler example, right? So let me start with the first derivative of this, right? So, yeah, let me do this. Yeah, the first derivative of this here is, sorry, yeah. So how does diff works, right? So diff, you pass the expression you want to differentiate, right? And then you pass the variable that you want to differentiate with respect to, okay? So I want to take this expression here and derivate it, differentiate it with respect to x, okay? When you do this, you get yeah, but I didn't include, wow, this is a bit weird, right? So let me do the original expression first. I think I get something out here that I shouldn't. So this is the original expression, okay? Just to, yeah. Yeah, I must have get something out by mistake. So this is the original expression, is x squared times a sine of x. If I differentiate it a single time, it gives you this expression here. And now what if I want to calculate, for instance, the third derivative? So I want to derivate 3 times with respect to x, okay? So I have this, I can pass another argument here, that is the number of times I want to diff, okay? So in this case, the diff is 1, okay? If I do nothing, if I have just x here, if I pass x and then 3, it means take the third derivative of this expression with respect to x. Okay? Yeah? Easy to use? Yeah? Okay. A few more examples, right? So I can take derivatives with respect to different variables, okay? So if I have this expression here, for instance, I can diff this with respect to x. I think it's the first one. And the second one is the derivative with respect to y, okay? You see that you have different results, right? Here, when you diff with respect to y, this x squared term goes away. And when you diff with respect to x, this term goes away, okay? So you're left with 2x, 3y here, and 3x, 3y squared here, okay? Yeah, so even if you're not very familiar with derivatives, you can use this to just get it immediately, even for complicated, yeah. And now also you can this is the mixed second derivative. Okay? Suppose that you want to diff with respect to x and then with respect to y. How do you do that? You pass the expression and then x and then y. Okay? This works. Okay? So you do a second derivative here that is a second mixed derivative. Okay? See? Okay or not? Yeah, easy so far? Yeah? I'm not so sure if this is unfamiliar to you. Maybe you're not so familiar with calculus itself, right? So this is a different problem than this is not a SimPy problem, right? It's a calculus problem. But so far, so good? Questions? Okay, so these expressions here were easy to derive, right? Let's see some a little bit more complicated. So if we take this expression here, that is an r cosine of log of 1 over x squared. So this is one that needs a lot of work in your calculus 1 course, right? So when you derive this, you get this expression here, you see? So yeah. So this is possible to do with simple rules that you learn in calculus, but it's quite some work, okay? And then you have this other one here. I have a fraction that contains a fraction in the denominator, and then another fraction, and then another fraction. So you have to calculate this, you have to expand, and then do a lot of quotient rules and so on. If you derive this, it gives you this answer down here, okay? Yeah, so it can, you know, get a lot of work, right? Yeah? Question, yeah.
By default, the log is base 10 or base E?
Yeah, log, when you just log it, always natural base. If you want log base 10, you have to use, I think, the function, I think there's a function log 10, I hope. Let me check here. Oops. Sorry. sp.log. No, it doesn't have a function log 10. I think you have to do the old school way of dividing by the log of 10. Yeah. So all logs are natural log, okay, with base E. Okay. Okay. So now let's go for integrals. Okay, integrals. So usually if you are going to do integrals, you have. For instance, I have this function here, s squared plus cosine of x, and you use integrate, the expression you want to integrate, and the variable you want to integrate with respect to. So this is the integral of this function dx, okay? Dx. This is an indefinite integral, okay? An indefinite integral. It doesn't have limits during the integration. So it gives you back not a number, but a function, okay? A function of x. Right, so like this, okay? And you see that, so the integral of this function, indefinite integral of this function is this other function here. But you remember from calculus that all indefinite integrals are defined up to an arbitrary constant, right? So you always have to some plus constant at the end, right? So SimPy doesn't add this constant automatically for you. You have to remember that there should be a constant over here. It gives you one function, not the set of all indefinite integrals, okay? Definite integrals are similar. You pass now the expression, and then you have as a secondary argument, instead of having only x, you pass a list here with x, the lower limit and the upper limit, okay? So this is the integral of this expression with x going from 0 up to 2 pi, okay? So pi is defined as sp.pi, okay? So this is a special variable here. Please do not define anything called pi that is not pi in your code, right? So otherwise it will be a mess, okay? So this integral here is essentially this calculated from 0 to 2 pi, and then this gives you a number, okay? This gives you a number now. This is 4 pi, okay? So this is definite integral, right? Now let's look at a few more complicated examples. I think this one, it was pretty simple to do by hand, but then for instance, if you have this log here, integrating, you have this. If you try to integrate exponential of minus 2x squared, you see that this is essentially a Gaussian function, right? This doesn't have a simple antiderivative, but it can be written in terms of ERF, right? That is called the error function. Okay, that is another special function that appears a lot when you do probability and statistics, right? Probably you have seen this in the statistical modeling course, I hope. Yeah, so this error function, the integral of the Gaussian. Yeah, or I'm not sure. But have you seen this or not? The integral of the Gaussian. I think it appears somewhere over there. Okay. Sorry, don't hear. I can hear you, sorry. Yeah, use the mic, please. Yeah.
Just to be sure, the integral of the Gaussian function is the probability of the interval you want.
Yeah, if you calculate the integral between a lower limit and an upper limit, this is the probability of the value being between these two numbers. Yeah. Yes.
Okay.
So if you have seen this in the statistical modeling course, what you have done is essentially calculating the value of the definite integral of the Gaussian function.
Okay.
Yeah? But then probably in R you just use the G-norm and P-norm functions that does those calculations behind the hood, okay? So it does that for you. Okay. Okay, and now there's something tricky here. I have here a function that doesn't have an integral, even in terms of the usual special functions, right? So this is the integral of the square root of cosine of x squared, right? And you see that when you don't have an integral, the integral is not be written in terms of these functions. SymPy will try a lot of different methods, and this takes like forever to run, right? And then when it finishes, it just gives you back the integral, okay? But then, yeah, so you see, it didn't perform the integral, it just gave me back an unevaluated integral, okay? So this can happen, okay? And usually if it takes a long time, it's probably because you have the situation, okay? It's funny that derivatives, you can always calculate a derivative of pretty much any function, okay? Any function that is continuous and derivable, okay? But then for integrals, there are many functions that you look like, you see, square root of a sine of x squared doesn't look a lot uglier than other functions we have seen here, right? So, right? It doesn't look uglier or, you know, but then it doesn't have an integral in terms of elementary functions, but others have, okay? So it's sometimes hard to predict which ones don't have an integral, okay? Yes?
But even if the integral doesn't have a primitive, if we ask it for with limits, does it do a numerical integration?
It doesn't, no, it doesn't do numerical integration. So for instance, let me do this here, right? So you're asking, well, what if I wanted to do this just between 0 and 1, right? So this is definitely doable, okay? Yeah? Right, so if I do this, it gives me back the same stuff, okay? So it doesn't do, so SymPy is a symbolic Python, right? It only does symbolic calculus. It doesn't do numerical calculus, okay? So of course you can solve this integral numerically, yes, okay? There are methods, and we are going to see that SciPy library has methods for calculating this, right? But SymPy doesn't use those, okay? SymPy doesn't mix numerical methods with symbolic methods. It only calculates the finite integrals by calculating the antiderivative and then substituting the limits, okay? And not in any other way, okay? Okay. So let me, yeah. Okay, so limits now. Limits now. So one thing to note is that infinity is represented by OO, two O's, right? So this is infinity. And here I use this other function L, the limit with a capital L. This is an unevaluated limit, okay, just to be able to express this easier, okay? So, so how do you do a limit? You have to write limit, the expression you want to take the limit, the variable you want to take the variable you're going to change as you change, the variable you want to take the limit of, and then the value to which this limit goes, right? This variable goes. Okay, so this is with x going to infinity, okay, plus infinity. Okay, if you wanted to go to minus infinity, you can put a minus here. Okay, so let's see what happens here. So here it is, right? So the limit of 1 over x with x going to infinity gives you. So this is the unevaluated one that is to show this stuff here, and this is the evaluated one that gives you 0, okay? And so on. So x over sine is the fundamental one of the fundamental limits. This gives you 1, okay? And if you do this 1 plus 1 over x to x, this is another fundamental limit. This gives you e, right? So the imperial number, okay? Yeah, so so you can do limits, okay? And finally, we have differential equations, okay, differential equations. So I think by now you have some notion what are differential equations in Roberto's course, yeah? A little idea of how they work, okay? So, okay, so now what is different about differential equations compared to algebraic equations? Okay? Differential equations are equations where you are solving for, what you're looking for, the solution is no longer a number, but is a function, okay? So you have an equation that involves a function, its derivatives, and the solution to a differential equation is a function, okay? So now my symbol, the thing I want to solve for is not a number, now it's a function. So I want to create a symbol that represents an unknown function, okay? Yeah? So how do I do this, okay? So I use the same symbols function as before, okay? But now I called with this this argument CLS here, that is for class, right? Class equals to sp.function, okay? Dot function, okay? And this tells me that f and g are two symbols whose name are f and g, but they are not numbers, they are functions, okay? Yeah? And so they are going to be treated as a function by SymPy, okay? So what is a function different from a number, right? I can call the function of an argument, okay? So I can write, for instance, f of x, you see? And I can calculate the derivative of f of x with respect to x, okay? So this gives me ddx of f of x. I can calculate the integral of f of x with respect to x, right? So this gives me the integral of f of x dx, okay? And this is in this form here because we don't know what is f, okay? We don't know which function it is. So I cannot really perform this derivative or this integral without knowing what f is. So I just have the expression like this, okay? Yeah, clear? So f then is an unknown function, okay? Now, to write down our differential equation, right? So suppose that I want to solve this. I think this one you saw already, right? So the linear differential equation, the exponential equation, okay? And what happens here, right? So I use this EC function here, okay? So this is for equality, right? And here I will define a new symbol R to be this R here, right? F and X are already defined. So I have that my differential equation is EC, the GIF, yeah, I wrote it like this. I put all expressions I can, instead of putting GIF expression X, I can also do expression dot GIF X, okay? This is the same thing. I would also the same thing here, this is the same as GIF of this expression, with respect to x. Okay, so these two things here are the same thing. Okay, right? So yeah, actually I have an SP. Okay, so I'm saying, okay, the derivative of x with respect to x, of f of x with respect to x, is equal to r times f of x. Okay. One thing to remember here that is important is that you have to use this f of x thing all over, okay? You cannot just write f. I have to say f of x because we didn't even, when we defined f over here, we didn't even tell SymPy if f is a function of x or of y or of both x and y or what, okay? So whenever we use this, I have to tell it that f is a function of x, okay? So I have to tell here as the derivative of x, f of x, and here r times f of x, okay? Good? And then when we do this, right, so I have this, so this equality here, right, I'm displaying here, this equality is our differential equation here, okay? And how do I solve this now, okay? I told this function called gsolve, okay? Gsolve is for solving differential equations, okay? Or usually ordinary differential equations, ODEs, okay? And I just call this for now with the expression, and then it will give us back the solution. It returns another equality. What is the equality? F of x equals C1 times the exponential of r times x, okay? And you see that there appears here a new variable that we hadn't defined before. That is C1. What is this? It's an arbitrary constant, okay? I think you have seen this from the other class or not, from the other course or not. So here we have, we don't have an initial condition for these differential equations, right? These differential equations. So when you don't provide initial conditions, you end up with arbitrary constants that will be fixed by providing initial conditions. So this is what we call a general solution, okay? This is, so any value of C1 here gives me a different solution to that equation. If I give an initial condition, this sets me a particular solution, a particular function. Is this make sense? Sense or not? Or am I going too deep on calculus? I'm kind of hoping that Roberto kind of explained this before. Yes or no? Yeah? So if you haven't, I think if you haven't seen this before, it will probably also appear in Roberto's course. I hope. Okay. And finally, I have here another. Oh, okay. Now I have repeated thing here. Okay. You're doing chess. Yeah.
Can you show us an example when you give an initial condition?
Yeah, I'm going to show that in a moment. Yeah. Okay. So this is another equation here, now a much more complicated one. Okay, this is a second order equation with a non-homogeneous part here and so on, right? And when you do this, so this is the equation, right? This is the equation, so you see that it's a second order equation and a bit more complicated. And this is the general solution. Since it's a second order equation, now you have two different arbitrary constants, right? But if we also pass initial conditions, right, how do you do that? Like this, you have gsolve your differential equation, and now you have this argument here called ICS for initial conditions, okay? And here you say, well, f of 0 is 1, and f dot or f prime at 0, so the first derivative of f at 0 is 0, okay? When you pass this, okay, so these are the initial conditions for this differential equation here, okay? So for second order equations, I need two initial conditions, not just one, okay? And then what happens is that now it will give me a solution without any arbitrary constants left. So you see that this solution here is the same as this one, you see? Compare the two of them, they're the same. But now I see that C1 is half and C2 is minus half. You see? So it when you give it initial conditions, it calculates for you the value of the arbitrary constants. Okay? Nice? Okay, good. And now the final thing here is, okay, now we can use this. Okay, there are other stuff to learn still about SymPy. We'll have another class on this, but how do you, if I have a function, or if I have an expression that I calculated somehow in SymPy, okay? I use it integrals, solving differential equations, I don't know, did some calculation, right? But then I want to do numerical stuff with it. I want to calculate it in a set of points, I want to plot it, I want to numerically integrate, I want to explore it in a different way that doesn't use SymPy functions, but use, for instance, NumPy functions, okay? Use arrays on it and so on. Okay, how do you connect SymPy to other functions in Python? Okay, because x now my x, my y, my variables here, they're not arrays, they're not numbers, they are SymPy symbols. Okay, so to use this, for instance, if I have an expression here, okay, so I don't know, expression is x squared plus 1, okay? I want to, naturally, suppose that I want to calculate this expression for different values of x, right? I would want to do something like this expression calculated at x equal to 1, for instance, right? And I would expect this to give you 2, right? But you cannot do this, right? If you do this, I can even try this here, okay? So let's add, yeah, if I do this here, okay? This gives me an error because this is not callable, okay? So this is not Esprit. Esprit here is an expression. An expression is not a function, okay? It's not a, it is kind of a mathematical function, but it's not a Python function. You cannot use it as a function, okay? Yeah, so this is what we are trying to work around now, okay? So what do? You do, there's a function called lambdify, okay, this is a kind of funny name. This is because of what is called lambda functions. Okay, I'm not going into detail about what is a lambda function here, but there's this function called lambdify, okay? And now you see that besides SymPy, I'm also importing NumPy and matplotlib here. Here I have my expression, okay? And now I'm going to call lambdify. Lambdify takes 2 arguments. The variable that I want that will be the argument of the function, and the expression, okay? And the expression, right? And now this f here is a function, okay? F now is a regular Python function that you can call, okay? So for instance, if I have here, I told xx not to mix with the x that is a symbol, right? So xx now is a NumPy arrange, okay? So this goes from 0 to 1 in step size of 0.01, and y is f of xx, okay? And I can plot this. You see, now I can call f of x, okay? So let me, for instance, I can call f of, I don't know, f of 2. This gives me a number, okay? I can calculate f of an array. F of an array returns me an array just like NumPy functions, okay? Yeah, so I can use f as a function. Not only, I think the default set is to use NumPy functions, okay? So it's already set up for using together with NumPy, okay? Yeah, so you can use it on arrays and so on, okay? And then I just do this, for plotting, okay? For plotting. So I do this here, okay? I'm not going to do anything more complicated than that, but is it clear what I did here? So I transform it, this part here actually, right? I transform it, an expression, into a function, okay? And now I use this function, I calculated this function over a vector, and then I plotted the x vector against the y vector here, and so this is the function, the graph of x squared plus 1, right? Between 0 and 1, okay? Yeah. Here I have another example here that as a bonus, if I have 2 variables, okay? If I have 2 variables, for instance, this expression here with 2 variables, okay? I call the function, and now the first argument is not just x, it's a list here with two variables, x and y. Okay? So now f is a function that receives not one, but two arguments. Okay? X and y. Okay? And now this is a bit more complicated. I'm not going into detail here. So this is the recipe for doing, since this is a two variable function, to plot it, I have to plot it a 3D surface, right? So this is the recipe for plotting a 3D surface. I'm not going to explain this. I think we are going to embed later for this kind of stuff, right? But this is a 3D plot here. It's a nice surface, okay? So this is x, this is y, and then the z-axis, the vertical axis, is the value of this function, okay? So essentially, but just to remember then, this is, I call this f also. Yeah, I also call this f. So f now is a function that receives two values, okay? So I pass it two values, it gives me some result here, okay? So, you see? Yeah. So and then I use the fact that I can pass not only numbers to this, but also arrays to build this plot here, okay? Not going into detail of how exactly to do this plot, okay? Okay, questions? Yes?
What exactly is a mesh grid?
What exactly is what?
What is a mesh grid? Like
yeah, this is the kind of this is the thing that I did, that I said that I'm not going into details, right? So this is this is how you build this thing here. A mesh grid takes an array. So I think the easiest explanation is printing this stuff, right? So let's do this, okay? So this is if I do, what is x is, oh, this is too large to see something, right? So let's do something much less nice here. So let's go from half and half, okay? So this is, so the plot will be earlier, but then this will be simpler to see, okay? So this goes from -2 up to 1.5, okay? This is x. And if I print now y, you see? It's this, okay? Now, if I do this mesh grid here with of x with y, right? What this gives me is a matrix with the values of x and a matrix with the values of y for each point in this plane here. So if I look at this plane here, you see this is a matrix where along each value of x is a constant, but it changes with the value of x, and the same for y, right? So this gives me the locations of the points in this plane here, okay? So this is for x, and this is for y. So this is what mesh grid does. It does, so you see for x it's constant along columns, for y it's constant along lines, and this is what I need to do in order for each of those points to calculate the value of z, okay? And then I plot plot surface here, plot x against y against z, where z is f of this stuff here. You see, so this is the way to do 3D plots, okay? I have to calculate for each pair of values, you see, for, yeah?
Yeah, I understand, thank you.
Okay, good. Okay, people, so let's go for exercises, yes? So I wanted to have more time, but now we have 45 minutes, okay, for exercise 2. Okay, I know that we haven't actually finished the first one, okay, I know that. We're going to talk about both exercise 1 and 2 on Monday, but I want us to start now on exercise 2, okay, if you haven't yet, okay? So I think this is quite shorter, quite faster to do than the other one, but let's try to do it now, okay? Yeah? Okay, let's work, yes.